299, 300. So yeah, this is exactly what we're talking about today. Crankshafts. As a matter of fact, I decided to start a whole new series today, and I'm unofficially gonna call it the Engine Bootcamp. And in it, we're gonna cover a whole range of interesting and important topics. So when all of this mess is over, we're gonna come out of it as smarter petrolheads. And we're starting with this, the very heart of the internal combustion engine, the crankshaft. And after watching this video, you're gonna know all about the different types of crankshafts, their disadvantages, their advantages, how crankshafts are made. You're gonna hear terms like crank fillet, crank radius, crank throws. We're gonna talk about lubrication, balancing, counterweights. You're gonna hear terms like knife edging. Yeah, basically everything you need to know. Now, I'm willing to bet that when you think of a crankshaft, you think of, well, this thing, and that you strongly associate crankshafts with internal combustion engines. Well, the truth is that crankshafts are way older than internal combustion engines. As a matter of fact, they're ancient. The first instances of a crankshaft date back as far as 200 years BC in the Western Han Dynasty in China. Here, crankshafts were used to hand operate a quern. A quern is a primitive stone tool that's used to grind cereals and various foodstuffs. But all crankshafts, whether those on the hand-operated querns of the Western Han Dynasty or those inside a 10,000 horsepower top-fueled dragster, have the same purpose. They'll do the same thing. They convert reciprocating motion into rotary motion. Inside an internal combustion engine, the up and down motion of the pistons is converted into rotary motion by the crankshaft and then transferred through the flywheel and the clutch and the transmission all the way to the wheels of your car or motorcycle. This principle of converting reciprocating motion into rotary motion was widely used throughout history. Here's something from the Romans. As you can see here, the rotary motion of the watermill is converted into reciprocating motion via a crank and an actual connecting rod, with the end result of sawing logs in half. And while the purpose has remained the same, leaps in technology resulted in a massive evolution of the crankshaft, from a simple wooden hand-operated tool to a high-precision, high-strength metal piece of amazing engineering capable of sustaining thousands upon thousands of horsepower and prolonged exposure to very extreme forces. Now, before we dive deeper into the world of the crankshaft, first we have to know what is what on a crankshaft. So let's get our crankshaft again and let's check it out. Now, all internal combustion engine crankshafts have main journals and rod journals. So these are the main journals. Now, the main journals is what the crankshaft itself rotates on. And the crankshaft is held in the engine block at the main journals by the main journal bearing caps. These journals, which are usually smaller than the main journals, are called rod journals. They're also known as crank pins or big end journals. They're called big end journals because this is where the big ends of the connecting rods are connected. The rod journals are connected to the main journals via crankshaft webs. Now, the distance between the main journal center line and the center line of the rod journals is called the crank throw, aka crank radius. And this measure determines the stroke of the engine. It determines the up and down distance of travel of the piston. The stroke of an engine is always going to be 2 times the crank throw. At the end of the crankshaft, the butt of the crankshaft if you will, we are going to find a flywheel flange. This is where the flywheel is bolted onto. The flywheel, with its heavy round mass, has the task of smoothing out the pulsation of the combustions inside the engine. These pulsations occur at different times, and without a flywheel, the engine would feel much less smooth. On the other hand of the crankshaft, we have the nose, and this is where the crankshaft pulley is attached to. These big chunks of metal are the counterweights. Now, the operation of an internal combustion engine generates strong rotational forces, and the mass of the piston pin, and the rings and the connecting rod moving up and down at high speeds generates a very significant force that is exerted onto the crankshaft. The counterweights have the task of balancing out these masses and forces. We will talk more about counterweights later in the video. Now, the holes that you can find in the rod and main journals are oiling holes. Engine oil is picked up from the sump by the oil pump and sent through the block to the crankshaft. The oiling holes on the crankshaft have the task of creating a film of oil that prevents metal-to-metal contact between the crank journals and the rod and main bearings. Another very important design element of the crankshaft is the radius fillet. Engineers take great care when designing this because a proper radius fillet is key to a crankshaft not breaking apart. The radius fillet is key because it spreads the load and relieves the stress in what would otherwise be an extremely common stress fracture point in pretty much every crankshaft. Something that is machined at a perpendicular, at a sharp angle, is much more prone to a stress fracture when compared to something that has a fillet instead of a sharp angle. So now that we know what a crankshaft is and what it does and what are its parts, we're going to find out about the forces acting on the crankshaft. Now, the most obvious source of forces acting on the crankshaft, of course, come from the combustion generated by an internal combustion engine. Now, modern spark ignition petrol engines that are naturally aspirated usually generate combustion pressures in the neighborhood of around 100 bar. Compression ignition engines and forced induction engines usually generate twice that, around 200 bar of combustion pressures. Now, a 100 bar combustion pressure acting on a 4-inch diameter piston, which is around 10 centimeters, is going to generate a force of around 18,000 pounds. That's around 8 tons. To put this into perspective, the best and strongest boxers in the world, their punches usually struggle to generate around 1,000 pounds. That means a naturally aspirated petrol engine generates forces that are 18 times stronger than the strongest punches in the world. Compression ignition engines such as diesels and forced induction engines generate 36,000 pounds of force. That's 36 times more than the strongest punches in the world. And the crankshaft, being connected to the piston via the connecting rod, is subject to these punches thousands of times per minute as the engine reaches ever higher RPMs. Think about that next time you're cruising down the highway. But it gets even more dramatic. Most engines today are multi-piston engines. That means they have more than one piston per crankshaft, and different pistons are doing different things at different times in the engine. One is accelerating, the other is coming to a sudden stop. So what they're trying to do to the crankshaft is basically they're trying to tear it apart all the time. And surprisingly, they almost never manage to tear the crankshaft apart. And unless something goes horribly wrong elsewhere in the engine, the crankshaft is almost never going to fail. It's going to survive an infinite number of these extremely strong punches before it comes to the end of its lifespan. And combustion pressure generated forces are just one part of the forces acting onto the crankshaft. It also experiences primary and secondary shaking forces and primary and secondary rocking moments and a bunch of other stuff. So it really is going through hell all of the time. And this is why it's absolutely imperative that the design and the manufacturing process of a crankshaft is really good so that a crankshaft can survive all of this hell for a very long time. When it comes to the manufacturing of crankshafts, there are three main manufacturing processes, and they greatly determine the strength and performance potential of a crankshaft. The three manufacturing processes are casting, forging, and CNC machining. Casting is by far the most cost-effective process when it comes to manufacturing crankshafts. The downside is that in general, cast cranks are pretty weak. They're very brittle. Brittle meaning that they have a low tensile strength and a low ductility when compared to forged cranks or cranks machined out from a billet. Cast crankshafts are made by casting molten metal into a mold and letting it set. This usually results in a pretty random grain structure. Grain structure is the distribution and orientation of metallic particles within a metal part, and it greatly influences the strength of that metal part. Now, a random grain structure usually results in a pretty weak and brittle part. When it comes to the materials used, cast cranks are most often made from nodular iron or steel, and they have a typical tensile strength of around 60,000 to 100,000 psi and an elongation rating of around 2 to 3%. Now, cast crankshafts used to be pretty common in car and motorcycle engines, but nowadays you'll be hard pressed to find a cast crank in a modern serious engine. Nowadays manufacturers usually rely on forging for their crankshafts, and cast cranks are usually reserved for lawnmowers, mopeds, low displacement scooters, and chainsaws. The forging process involves a large crankshaft-sized billet being heated up to around 2,500 degrees Fahrenheit. The heated up billet is then put in a giant press, which has dies in it. The press then applies anywhere from 150 to 250 tons of pressure to shape the billet into a rough forging. The rough forging is then machined and heat treated to produce a finished crankshaft. You can tell a crankshaft is forged by looking for signs of grinding on it. Now, during the forging process, excess material known as flash comes out of the forging dies. This then needs to be ground away, leaving behind a telltale sign of a forged crankshaft. The forging process itself significantly compresses the grain structure of the forged crankshaft, and it creates a much more uniform grain structure compared to a cast part. And this means that forged crankshafts are typically not just stronger, but significantly more ductile when compared to cast crankshafts. Now, forged crankshafts can be made from a wide variety of materials. OEM crankshafts are usually made from plain carbon steel, usually the 1053 or the 1045 alloy. Now, the tensile strength of these alloys is usually around 110,000 psi, and while this doesn't seem that much more when compared to a cast crankshaft, it's the ductility of forged crankshaft that is much better when compared to cast ones. A step up in terms of forged crank alloys is 5140 chromium steel, and it's usually rated at around 150,000 psi tensile strength. Beyond that, we have alloys with even greater chromium and carbon content, such as 4140, and these are often used for most high-performance forged crankshafts, and they are rated at around 150k psi. Top of the line racing forged cranks usually feature 4340 alloys, and these are even stronger and tougher, and they are usually rated at around 140k psi. When it comes to billet crankshafts, there's no forging or casting. You simply take a billet and you machine away until you're left with a crankshaft. Naturally, this process takes a long time and a lot of material gets removed. And this is why billet crankshafts are usually pretty expensive and often reserved for racing and other extreme applications. The great thing about billet crankshafts is that you have infinite design possibilities. You can make the trolls as long as you want to, you can make the journals as thick as you want to, and the process is suitable for custom one-off crankshafts. which isn't the case when it comes to forging or casting. Very large tooling investments are needed for forging and casting, and these are justified only when a large-scale mass production takes place. Now, during the forging process of a crankshaft, the grain structure of the metal gets deformed, reshaped, and stretched at very high temperatures. This leaves some residual stress in the metal. Now, in contrast to this, billet crankshafts get to retain the grain structure of the metal, and it remains unchanged without any residual stress. Now, both forged and billet crankshafts get machined, but the machining is actually seen as less disruptive in the case of the billet crankshafts, and they get to retain an optimal grain structure. Another benefit of CNC machining is that it's very precise, and it enables very precise shaping and location of the crank throws. Now, this enables higher strength and easier balancing later on in the process. Typically, billet crankshafts are made from the 4340 alloy or better, and they usually have a tensile strength rating of around 160,000 to 165,000 psi. Once a crankshaft has been machined, it often undergoes heat or surface treatments. The goal of these is to stabilize and, more importantly, harden the surface of the metal. This makes it more impact, wear, and fatigue resistant, and significantly increases the lifespan of the crankshaft. Now, modern cast crankshafts typically don't undergo heat and surface treatments. The manufacturing and subsequent machining process hardens the metal sufficiently, so there's no need for additional treatments. And this is good because it usually means that cast crankshafts can be remachined or reground without any need for repeated heat or surface treatments. On the other hand, forged crankshafts usually start out by being softer than cast crankshafts, and they do require heat or surface treatments. Most OEM crankshafts undergo something known as induction hardening. This is a no-contact process that uses an alternating magnetic field to rapidly heat up the journal surface of the crankshaft, thereby hardening it. It's sort of similar to how an induction stovetop works. Well, sort of. But it's great because it's really well suited to mass production. It's inexpensive and it's fast. And while it's more than adequate for most OEM and even performance applications, it does have a drawback in the sense that it doesn't heat up the entire surface of the crank evenly, which leaves behind some uneven stress areas in the crankshaft. And this is why extreme racing applications often rely on more advanced surface treatments such as tuft riding or night riding. Tuft riding immerses the crankshaft in hot cyanide compounds. This creates a thin layer on the surface of the crankshaft. This thin layer is very resistant to wear and fatigue. However, there is a drawback because tuft riding introduces a bit of warping to the crankshaft, and this must be addressed after the tuft riding process is completed. Now, night riding is the more common process when it comes to surface treatments, and it involves the crankshaft being heated up in a special furnace and then exposed to nitrogen and ammonia gases. These react with the carbon on the surface of the crankshaft, thereby making it much harder. Night riding doesn't penetrate as deep as tuft riding, but it does have the advantage in the sense that it doesn't introduce any warping to the crankshaft. Unlike induction hardening, both tuft riding and night riding harden the entire surface of the crankshaft evenly, so there aren't any uneven stresses left behind, and this makes these processes more suitable to the forces seen in extreme racing applications. However, it must be noted that any surface or heat treatment done to the crankshaft will be compromised when a crankshaft is reground, and in order for the initial wear resistance and hardness to be restored, a heat and surface treatment must be repeated after machining. As you're probably aware, engine oil is the lifeblood of any internal combustion engine. Without enough oil and enough oil pressure, almost any engine is going to fail pretty quickly. And this is why great attention is given to the design of the oil delivery system within a crankshaft. a typical OEM crankshaft is going to be cross-drilled. And this means that the main journals and often the rod journals will have two oil delivery holes in them. The journals are in effect cross-drilled. And this is followed up by a drilling at an angle from the rod journal to the main journal to create a path for the oil between these two journals. The drilling is then capped off like this. Oil holes on both the main journals and the rod journals are pretty much always chamfered. If you ever see a non-chamfered oil hole on a crankshaft, which is very rare even in cheap reproductions, walk away. An alternative to the cross-drilled design is a straight shot oiling design. When it comes to straight shot oiling, you won't find two holes on the main and rod journals of these cranks, but rather only one oil delivery hole per journal. And then you're going to see a straight, uninterrupted drilling between these two holes of the main and rod journals. And because of this, there's also no need to cap anything off. Now, straight shot oiling is seen as a superior crankshaft lubrication according to some. And this is because in a cross-drilled crankshaft, pressurized oil must enter the main journal and overcome the centrifugal force of rapid acceleration or RPM to reach the center of the crank before the oil can travel to the throw, i.e. the rod journal. Now, increased oil pressure is often used to overcome this centrifugal force, but in extreme applications, enough pressure sometimes cannot be generated, and this can result in engine failure. And while this argument is a valid one, and while in certain applications a straight shot oiling system may be superior, it's naive to issue blanket statements that all cross-drilled cranks are simply obsolete and that they shouldn't be used. I mean, the design has been around for decades and countless racing teams at the highest levels of motorsport have achieved countless victories with cross-drilled cranks in their cars, so they really can't be simply eliminated by blanket statements. Remember those crazy forces that we mentioned in the beginning of the video that the crankshaft is exposed to? Well, the counterweights have the very important task of balancing out these forces. Counterweights balance out the masses of the pistons and the conrods and the piston rings and the piston pin and their associated forces. Counterweights ensure that there's no vibration and that an engine runs smoothly for a very long time. And this is why often when a crankshaft is described, you're going to hear the term fully counterweighted. A fully counterweighted crank looks like this. A fully counterweighted crankshaft is going to have two counterweights opposed to each rod journal. An inline 4 crankshaft that isn't fully counterweighted is going to look sort of like this. A fully counterweighted crank is often seen as a superior crankshaft to a partially counterweighted one. It ensures a smoother running engine and a better ability to cope with extended high RPM operation. Engines that come with high redlines from the factory almost always have fully counterweighted cranks. Something else you're often going to see on crankshaft counterweights are holes like these. These are created during the manufacturing process at the factory when a crankshaft is spun at high RPM on a special machine which dynamically balances the crankshaft. It identifies points on the counterweights where weight needs to be removed in order to ensure a perfectly balanced crankshaft. Another important thing when it comes to performance engines and crankshafts is the shape of the counterweights themselves, and it needs to be as aerodynamic as possible to combat windage in the crankcase of an engine. Windage is the turbulent flow of oil-infused air within the crankcase that creates a significant drag on the rotational motion of the crankshaft. A more aerodynamic shape of the counterweights is going to ensure less drag. And this is why you will sometimes see crankshafts intended for performance use being knife-edged. Knife edging means creating this sort of sharp, knife-like shape on the counterweights. The goal of the shape is, of course, to reduce the drag. On the other hand, billet crankshafts are often going to have these sort of aerodynamic shapes already incorporated in their counterweight design. Now, racing crankshafts aim to be as light as possible, and this is because lighter engine internals mean a more rev-happy engine and a better throttle response. And this is why you will sometimes see racing crankshafts having drilled crank pins or a reduced number of counterweights. Now, the comparison between Flatpoint and Crossplane crankshafts deserves an entire video on its own, so here we're going to just briefly summarize the two types and look at the pros and cons of each type. Now, Flatpoint crankshafts, as the name suggests, they're in a single flat plane. The rod journals are offset 180 degrees from each other, which means that both the main journals and all the rod journals are in a single point. Hence the name, Flatpoint. On the other hand, a crossplane crankshaft has the rod journals offset 90 degrees from each other, which results in the rod journals being in two different planes. And these planes are perpendicular to each other because the journals are offset 90 degrees, and hence the name crossplane. The two planes are crossing each other. Now, when it comes to inline-4 engines, almost all inline-4 engines feature a flat-plane crankshaft. Cross-plane crankshafts are extremely rare when it comes to inline-4 engines. On the other hand, V8 engines feature both flat-plane and cross-plane crankshafts. The traditional muscle car V8 almost always features a cross-plane crankshaft. And the cross-plane crankshaft means that there's a cylinder firing more often when compared to a flat plane crankshaft. And this is good because it creates a smoother running engine and a better balance between the two banks of the V8 engine. But typically, crossplane crankshafts are bulkier and heavier when compared to flat planes, and this makes them less suited for high RPM operation. On the other hand, flat plane crankshafts are better inherently balanced and they're capable of much higher max RPMs. They also sound very different. Flatplane crankshafts are also more compact by design, so you can make the engine smaller. A crossplane crankshaft is typically going to require a larger crankcase. On the other hand, the flatplane does have its disadvantages and typically it's going to be more prone to vibration when compared to a crossplane. It's also typically going to make less torque. And there you have it. Those are pretty much the basics when it comes to crankshafts. I hope you enjoyed this video and I hope you found it useful. Also, thanks a lot for watching, and I'll be seeing you soon with more content on the D4A Engine Bootcamp.